Okay, so in last video, we defined these steps to build a phase portrait that helps us classify equilibria Y star. And in this video, we're just going to go ahead and apply those steps in an example problem. And it's actually going to be the same example we talked about before, that logistic equation that I never defined as logistic. And if I have time in this video, I will talk about what the equation means and how awesome it is. So the example had been to think about dn dt equal to Rn times k minus n for some positive numbers r and k. And previously, in another example, we solved for the equilibrium. Oops. And we found that they were 0 and k. I'm not going to go through that again because we already did it, but that one gives us 0, that one gives us k. And this is going to be that like step 1 of the problem, is just defining those equilibrium values. And then step 2 over here was that we have to put all the y star in order on a number line. So mine are 0 and some positive number k that's bigger than 0. So there's my number line. This direction is positive, that direction is negative. And that is step 2. And then step 3 was that we have to examine the sign on every side of the equilibrium values. And so we're going to break this up into different cases of what we're thinking about. So we've got this side right here above k. That's going to be when n is bigger than k. This part right here in the middle is going to be when 0 is between k. And then this part down here below 0 is when n is less than 0. And so that's going to be enough for us to consider the behavior on every side of the equilibrium. And this is setting us up to do part 3, examine the sign on all sides. So when n is bigger than k, we've got k minus n has to be less than 0. So if k is 100 and n is bigger, it's like 150, then k minus n is minus 50, a negative number. And Rn is bigger than 0 because r is a positive number and 0 is over here. So n has to be bigger than that. So it's positive. And so taken together, that means that f of n is going to be less than 0, or a negative number. When I multiply a negative and a positive, I get a negative. Between 0 and k, in this region right here, I've got that k minus n has to be greater than 0. So if k is 100, n is less, it's like 50, k minus n is going to be 50, a positive number. But we still haven't crossed down below 0, so Rn is also still a positive number. And taking those two together is, I'm sorry, I shouldn't use that. It looks kind of like the less than, greater than signs. So taking those two together is going to give me that f of n, when I take the product of those two numbers, is greater than 0, or a positive number. And then finally for n less than 0, looking about down here, k minus n is going to be positive. So k is still 100, now n is negative 50, so 100 minus 50 is 100 plus 50, a positive number. And Rn is going to be less than 0 because r was positive and now n is negative down here, So that gives me positive times a negative is a negative. And so same reasoning, positive times a negative gives a negative means that f of n is going to be less than 0 or a negative number in this region. I do want to mention that if this like positive negative reasoning is hard for you, you can always just plug in numbers. Like you would have to say that like k is 100, which when you're doing your homework problems, usually they will use numbers instead of parameters. And here's 0, so you could just say, I'm going to test 50, 150, and negative 50. Plug them in. You don't need to do this generic case thing the way I am. If it's easier for you to calculate from a number, just make sure you pick numbers that fall between all your equilibrium values and above and below the largest and smallest. So then that was step 3, calculate all those signs. And now we have to move on to step 4, which was draw arrows up if it's a positive sign or down if it's a negative sign. So we're just going to come back over here and we're going to say, okay, in this region, I got a negative, so I draw my arrows down. And in this region, I got a positive, so I'm going to draw my arrows up. And then in this region, I got a negative, that means I draw my arrows down. If you have trouble remembering, your number line goes from negative to positive. So down, you're pointing towards the negative numbers. Up, you're pointing towards the positive numbers. So the direction matches the sign. Maybe that helps. And then let's just write, maybe right here. We know that all those little arrows were step 4. And so now step 5, we classify unstable if things go away, stable if they go towards, and then semi-stable if they go through. So in this case, when we look at n star equals k, we can see the arrows both point towards k. And just another piece of vocab for you, I'll always say stable, unstable, but you might hear this called an attractor. And that's just because solutions tend towards K. So if you can think about it kind of if you like drop the ball somewhere on this line and it follows the arrows, where's it going to go? Dropping the ball is picking an initial condition. Following the arrows is the solution to the differential equation. And we just want to know where it ends. So if you start between 0 and K, you tend to go up towards K. It's an attractive place for solutions to go. And I'm thinking about this as time develops. And then this means, not means. N star equals 0 is unstable. So if I look down here at 0, there's arrows pointing up and down. They're going away from 0. That's how I spelled repeller in my notes. I'm not sure if that's right. I never checked. But I will call this type of thing unstable. In other classes, you might hear it called a repeller. Solutions are pushed away from that value. So if you start down here, you're going to go towards negative infinity instead of moving towards 0. And we saw before, if you start in the middle here, you tend towards K, not 0. And this classification, stable, unstable, is the answer of this type of question of finding and classifying equilibria. So at this point, we're done with the problem. I did want to take a few minutes to tell you all about this differential equation. If you are just super crunched for time, turn off the video now. This isn't, you know, more important than you sleeping, but I still think it's cool and worth talking about. So this specific differential equation that I picked for this example is called the logistic growth equation. So you think about n being the size of a population, so like the number of people in a small town, and t being time, so like years. And dn dt means how does the number of people in the town change as time develops? And this equation says, well, it's going to be r times n, where r is like a growth rate. So the change somehow depends on the growth rate and how many people there are. And if we only thought about that, we would be saying every year the population grows at some rate r for the number of people there are n. That's what we call exponential growth. Every time you have more people, you have more that come from them later. That part that I erased, the k minus n, sort of modifies that and says, but it also depends on how far we are from some capacity k. And that's called the carrying capacity. It's how many people can physically live in the town. So if it's 100, it says there's 100 houses. Once you've passed 100, no more people can be here. So as we get like above k, if n is 150 and k is 100, this number's negative. It turns the whole term negative. It says, oh, now the population's actually going to go down. It has a negative growth rate. There's decrease in the population each year. But if you're below that k, like if you're at 50, then this number's positive and it pushes us up towards k. It says this year there's positive growth. dn dt is positive, means more people each year. And so that's why we have this behavior that the solution tends towards k. It's that like ideal balance of how many people can fit in this area. That's also why when I was talking about it, it was hard for me to remember to draw below 0, because to me it doesn't make sense to have negative people. But mathematically, if you have negative people, you will have more and more negative people based on this equation. So that's sort of what this equation means and why we studied it for this example. Explaining an equation like that is part of your first project. It'll be a different equation, of course. So I just wanted you to have sort of an example of how we talk about differential equations.